Okay, all right. Hi,
Sorry.
that's okay.
Please have a seat. All right, we're ready to go.
I guess.
After the introduction from up here. Well, welcome everybody who's here in person and also to the audience at home. It is my pleasure to introduce Joe Whalen, graduate student in my lab, who has done some fantastic work on very exotic molecules and using them to probe one of the more fundamental aspects of a very interesting and important subject of quantum many-body physics, and really trying to figure out the arrangement of particles on a very microscopic scale, which can be really important to tell the difference between a liquid and a solid and a gas, for example, which we're familiar with, but even more exotic phase transitions can be heralded by signatures in the spatial arrangements of the particles. And so he's developed some exciting new tools to allow us to look deep inside various kinds of complex materials and extract those properties. So very, very proud of what he's done, and I really look forward to hearing his presentation.
Okay, thanks, Tom. All right, welcome everyone. Sorry about the little delay, but like Tom said, my name's Joe Whalen, and I'm really happy to be talking to you today about probing some non-local correlations in strontium gases using ultra-long-range Rydberg molecules. And so, first, I'd just really like to acknowledge my committee and my group. So first, Tom Killian, my advisor, Barry Dunning, and Hanyu Zhu are here, and Hanyu so gracefully came onto the committee at the last moment. That was really nice of him. So, and particularly, I'd love to acknowledge the past group members from the Rydberg experiment, Roger Ding and Francisco Camargo, who helped build up the experiment and really set everything up the way it is now. And of course, the future people and current people in the lab who are all here today as well. So many hands make the load light, and I couldn't have done any of this work without you guys. So I'm going to give some introduction and motivation as to why this is interesting. Tom kind of just did that. And then I'm going to talk about our experimental apparatus a little bit, and then get into some results about probing correlations in thermal gases of strontium, and then talk a little bit about how we have a pathway toward probing a strongly interacting gas using heteronuclear Rydberg molecules. And so ultracold atoms are amazing. They're really great for probing fundamentally quantum systems. At these very low temperatures, the de Broglie wavelength of these particles spreads out, and the wave nature of matter really stands out. And everything happens in these ultra high vacuum chambers, so they have this exquisite degree of isolation from the environment, so all the evils in the outside world cannot come in and collapse the wave function. And also, we can very easily exploit the atomic properties of these systems and use electric, magnetic, optical, or microwave fields to tune interactions and things like that, which is our degrees of freedom you don't really have in, say, a solid state system. And then also we can use the internal states or internal degrees of freedom of atoms to read out information about the atomic state. And just here I have some lovely images, some of my favorite atomic physics images. So you have the first BEC in 1995, where the first degenerate quantum state of matter was created in a vacuum chamber, and then in less than 20 years or 30 years, we've gone from just making BECs to putting atoms in optical lattices to this amazing work where people can use a literal microscope and have single site resolution on an optical lattice. And our goal here, as Tom mentioned, is to develop a tool to probe spatial correlations in these many body systems. And so, what is a correlation? Well, really, it's any. In this case, we're talking about formally something like this, which is defined as an ensemble average over some creation and annihilation operators. But you can think of it more as a statement of say order or disorder, a quantification of order or disorder in one of these systems. And so these correlations are everywhere in physics. They manifest themselves in, say, magnetic ordering. In, say, like an Ising model, you have antiferromagnetic or ferromagnetic states or paramagnetic states. You get spatial ordering in, say, something like a lattice. Anytime you make an ice crystal or something like that, the atoms and molecules necessarily form this particular lattice and go from, say, a disordered state to an ordered state. And then even something as simple as quantum statistics, such as the fact that fermions don't want to be near each other due to the Pauli exclusion principle, that too is a form of spatial correlations. And people also talk about temporal correlations, such as photon arrival times, discrete conductance of, say, you have electrons going across a junction, or maybe even like a Henry-Brown twist type interferometer where you look at correlations in light from stars to determine the size of the star. In this talk, we're going to be really focusing on the spatial correlations, and in particular the ones that arise from quantum statistics. But measuring these correlations gives us really nice insight into properties of physical systems. So you can always write down a Hamiltonian, and well, if you can solve it, then you can say, okay, here's the energy spectrum. But when you start adding more particles and getting the Hilbert space becomes really, really dense, and knowing the energy of a state doesn't necessarily give you much information. And there might not even be that much difference between two eigenstates. But if you can look at, say, correlations, you can try to extract global properties of these systems and look at something, say, like an ordered or disordered or bunching, anti-bunching type thing. So here, like I said, we're going to focus on the pair correlation function G2, and don't worry about this too much, but really all it does is it quantifies the relative probability of finding two particles separated by a certain distance. And so we're going to use an atomic physics system. This is our table here, to probe correlations in a cold gas. And like I was saying, Bose-Fermi exchange statistics are pretty interesting. Of future interest is looking at a strongly interacting 1D system with our new optical lattice that we're installing. And really, we want to probe these correlations in situ. But that's a kind of an issue because everything is happening inside this vacuum chamber. I can't exactly go in and put leads on a sample to probe some kind of correlation directly. So that's not necessarily a problem. Atomic physicists tend to be pretty clever. So in the past, people have done used a lot of different ways to probe correlations in these gases. So one way was done by the group of Eric Cornell back in the early DEC days by looking at three-body loss to quantify the pair correlation function at essentially zero, at r equals 0. And then around the same time, people started doing what's called photoassociation spectroscopy, which we have a diagram here from Josh Hill's thesis from my group, where you excite at short range, low-lying molecular states to probe out the scattering wave function of two colliding atoms, and that gave people information about what the scattering length was and whether or not cold gases could be used to create Bose-Einstein condensates in the first place. And then more recently, as I pointed out at the beginning, we have the quantum gas microscope where you literally just take a picture of the lattice and then you can actually calculate correlation functions to all orders on the scale of an optical wavelength, which is around 500 nanometers to, say, a micron or so. And now I've left this suggestive looking hole in the middle of my plot here, and I propose that we could use ultra-long-range Rydberg molecules to fill this gap and use the tunable bond length that they have to probe correlations in this intermediate regime. And just to kind of give you a little menu of what's available, recently work from Jim Amon, also in our group, looking at halo dimers in strontium-86. Those are molecules that are very large and are very easily tuned. And you could, in principle, quench on interactions and study those with these ultra-long-range Rydberg molecules. We're interested in looking in the future at strongly interacting 1D gas, and also nodes in strongly interacting scattering wave functions. And so to understand what a Rydberg molecule is, you got to understand what a Rydberg atom is first. So a Rydberg atom is an atom that's excited to a high principal quantum number n. And here I have the spectrum for hydrogen. So you can see n equals 1, 2, 3, 4, and you can see that the binding energy is going down rapidly, and it goes down as 1 over n squared. And so the fact that this electron is so weakly bound has some pretty interesting implications. So even if the atom's not hydrogen, when the electron's really far away, all it sees is a +1. And so I would call that a hydrogenic potential. And the implication of that is that only a few parameters actually define all the properties of such an atom. In particular, the long lifetime which is for n equals 38, 21 microseconds, which is an eternity in atomic physics terms. They have huge polarizabilities due to electric fields that scale wildly as n to the 7. And all these properties, as you can see here, scale with the principal quantum number n. And the most important one for this work is actually the Rydberg radius, which scales as n squared. And if you consider the normal size of an atom is about 1 angstrom, at n equals 38, the electron orbit is now 2,000 Bohr radii, which is just absolutely huge. And so that's how we can really start making things interesting. So when you excite a Rydberg atom in a dense background, this Rydberg electron is now pretty far away from its parent nucleus, right? And so if you have another atom hanging around at about 2n squared at about 1 Rydberg radius, the electron can scatter off of this atom, and we parameterize that with this interaction called VEA. And a fellow named Enrico Fermi back in 1934 came up with, was looking at some people's Rydberg spectra and came up with an idea to model this interaction as a delta function parameterized by this scattering length A. And the sign of this scattering length determines whether your interactions are attractive or repulsive. And under a first order perturbation theory picture, so to speak, this atom here observes a potential that follows the shape of the Rydberg wave function of this atom here, of the electron. Okay, and so in the year 2000, now ultracold atoms have come onto the scene, and people are starting to get interested in what we can do with them. And a guy named Chris Green and a few other people really started taking this idea of the pseudopotential really seriously as a molecular potential, as something that can support a bound state. And so what they did is they simply took this is for rubidium, they took this potential, they know the scattering length, and they literally just plug it into Schrödinger's equation and out pops some eigenstates. And these little wave functions are literally molecular wave functions that have a bond length on the order of n squared. And in particular, I want to point out that it doesn't have to be n equals 30. It can be n equals 29, 35, 40, and all of these have this highly localized state. And so it's important to remember, though, that these molecules really can't exist outside of an ultra-cold system. Their binding energies are so small that even in the 3 Kelvin background of space, they would just be ripped apart by thermal energy. In 2009, the first Rydberg molecules were detected in rubidium by the group of Tillman Fow. And then in 2015, Brian DeSalvo and Jim found the first strontium Rydberg molecules, and we've been working on those ever since. And again, on the right here, I have a figure. So again, this Rydberg potential shown in black is just the modulus squared of the Rydberg wave function, and then in strontium we have a negative 13 Bohr radii scattering length, and we can see all these beautiful bound states that were calculated by Shuhei Yoshida, and correspondingly on the right is a preview of the kind of signals that we're going to look at, where I can tune my laser and I go down from the atomic Rydberg state and I can see a little series of resonances that correspond to the vibrational sublevels of this potential. And so essentially we can really select out the ground state here. And these molecules have also been observed in cesium and potassium, but in principle it's a universal thing. All atoms have Rydberg series, molecules have Rydberg series too, and as long as the electron scattering length is appropriate, you should observe some kind of bound state like this. And so I'm pointing at this bound state a lot because this thing are going to be our workhorse from probing correlations. So again, this molecule is a bond formed by the scattering between a Rydberg electron and a neutral atom, and you get this lobe at about 2n squared, which it tunes with the principal quantum number. And in order to make one of these molecules, not only do you need to conserve energy to excite the electron, but you also need to have 2 particles in this vicinity, in this highly localized region. And so that's how we're going to use them to probe these correlations here. So again, the nu equals 0, the ground vibrational Rydberg molecule state is highly localized at the Rydberg radius, like this. And in order to make one of them, you have to take, so this is a scattering wave function, so this is a relative probability of a pair of atoms, or it is the probability of finding a pair of atoms at a given distance. And you have to, what is the probability of finding 2 atoms here, and then you have to go up here. And so this is called a Frank-Condon overlap, but essentially you can think of, you have many different collision energies, which give you many wave functions to probe, and then when you excite a Rydberg molecule, you sample that Boltzmann distributed collection of wave functions down here and ask, who's there? Where are there particles here? And then you can change n and say, are there particles here, or here, or here, or here, right? And so I'm going to say it now that this is exactly quantified by G2, but we'll formalize this relationship a little bit later. And so this is a pretty interesting prospect because this probe can be non-destructive even though it's in situ. So when you make a Rydberg molecule, really we make only one at a time, and then we can blow it away very easily by using an electric field that doesn't perturb ground state atoms. This probe is fast. So on the Rydberg molecule, excitation time is on the order of 1 over the binding energy. So the typical binding energy is tens of megahertz, so that kind of speed. But in particular, that's important because that speed is a lot faster than typical motional timescales in a cold gas, and also faster than dynamical timescales that might be set by something like 1 over the chemical potential or 1 over the Fermi energy, which would be on the order of chemical potential for sure on the order of like kilohertz or so. And again, this is universal. If your atom definitely has Rydberg series, if the electron atom scattering length is attractive, then you should be able to make a Rydberg molecule. And that's what I think is pretty exciting about this. Okay, so now we're gonna move on and talk about the experimental apparatus, unless there's any questions. No? Okay. So in our experiments, we use strontium. Strontium is an alkaline earth atom, has 2 valence electrons, which enables us to excite to 2 different independent series, the singlet series and the triplet series. And that just refers to the orientation of the 2 electron spins. We can excite to Rydberg states using a 2-photon excitation. And importantly, there are 4 stable isotopes of strontium. We have 3 bosons, 84, 86, and 88, and a fermion with spin I equals 9/2, strontium 87. And then we can also trap mixtures, binary mixtures of these 2. So these 4 stable isotopes are pretty handy because we can produce many different types of samples. So for example, we can make what I would call a so-called classical gas that uses unpolarized strontium 87. So you have 10 different magnetic sublevels that don't exhibit Fermi repulsion when you have two colliding fermions in different spin states. You can also spin polarize this gas of strontium 87 and create a gas of identical fermions, which we would expect to have this Fermi repulsion. And then you can just as easily create a identical gas of approximately non-interacting bosons using strontium 84, and you can get really non-interacting if you want using 88. And that's just as simple as trapping them because this is a spinless ground state. And then if you want to, we don't have a Feshbach resonance, but because we can trap all these different combinations, we can essentially go to town and pick whatever interaction strength we want just by choosing our isotope combination. So if we choose 86-86, we get pretty modest interactions of 800 Bohr. And then if we go 84-88, we get some really big interactions, which we'll talk about a little bit later. So to get these samples ultra cold, we begin by trapping strontium in a so-called broadband MOT, where we have 6 specially tuned laser beams using the radiation pressure of their light to hold the atoms in place in concert with a magnetic field gradient. And that MOT operates on this broad 461 nanometer transition. And so this is a nominally closed transition, but some atoms leak out into this metastable triple P2 state. And so that helps us load a lot of atoms, and they can sit in the dark in this magnetic trap. and then we apply a repumping laser on this transition here at 481 nanometers, and then load our atoms into a narrow line mod that operates on this narrow transition here. And so now we can't take pictures with our cell phones, so we use what's called absorption imaging, where we shine resonant light onto the atoms and observe the shadow that they cast onto a camera. And this mod allows us to get down to about 1 microkelvin, from where we can load into what I would call a conservative potential into an optical dipole trap, which is formed at the intersection of 2 tightly focused infrared beams, each with about 4 or 5 watts of optical power. So wear your safety goggles. From there, we can cool our atoms even further by systematically lowering the trap depth and allowing hot atoms to leave and leaving cold atoms behind. And depending on where we stop that process, that sets the final temperature of the sample. And then in order to measure the number of atoms and the temperature, we let the atoms fall down under gravity and let them expand, and we take another picture that looks like this. And this is about 300,000 atoms at 250 nanokelvin. This picture was provided by Sumya yesterday. So the experiment's still working. And so importantly, we can measure the atom number and temperature, but we also know information about the trap, so then we can back out what the cloud density profile was in the trap using the trap parameters. Okay, and so I'm just going to briefly talk about mixtures. It's not actually all that different than laser cooling a single isotope. Instead of going straight from the blue mott to the broadband mott to the narrowband mott, we use the fact that the broadband mott leaks into the magnetic trap and store 1 isotope of atoms there and then load in another. And then we can repump both of them simultaneously using our repumper, and then everything else just happens in parallel. So again, mixtures are going to be important here because, for example, you can't cool down spin polarized 87 with itself because there's no collisions, because they're fermions. So you load in some 84 and use it as sort of a refrigerant to let 87 cool down. And again, you can use a mixture to tune the interaction strength. And then once we're done getting whatever sample we want to whatever temperature we want, we can always selectively eliminate one of the isotopes that we don't want in the trap. And so, okay, so then for Rydberg atoms of strontium, as I said, we use this 2-photon pathway by using the 689 to the triplet P1, and then go up to the triplet S1 series here using a 320 nanometer photon. So the 689 nanometer photon always has a fixed frequency. It's detuned a few tens of megahertz away from the triplet P1 resonance. And then we scan the UV photon to select the principal quantum number and then detune down and pick out our Rydberg molecules from there. We can create Rydberg excitations using any isotope, and then even can, and therefore Rydberg molecules of every isotope, I suppose. Now, the way we detect these, as I said, we only typically make one or two Rydberg atoms or molecules per excitation, is we have in our chamber a series of electrodes that, can you guys see that? Red? Okay. We have a series of 8 independent electrodes inside our vacuum chamber to which we can apply independent voltages that we can use to create electric fields. And as I mentioned, Rydberg atoms are extremely sensitive to electric fields. So here we have, let's say, 500,000 atoms at 500 nanokelvin in our optical dipole trap. And then we shine on our 2-photon excitation. And typical parameters, we use a 5 microsecond laser pulse and maybe 1 milliwatt or so per beam. And we turn off the optical dipole trap so to prevent an AC stark shift for the technicians in the room. And this excitation, if it's on resonance, creates a Rydberg atom. And this Rydberg atom is hanging out in here. And as soon as it's created, essentially we ramp on a big electric field and liberate the electrons from their parent nuclei. And so a Rydberg atom is ionized at a relatively modest electric field that goes as 1 over n to the 4. And so for n equals 38, it's about 225 volts per centimeter. And that would correspond to us applying a differential voltage of about 2 kilovolts here to really make sure we're ionizing everything. And then the electrons fall onto a microchannel plate detector where they are counted and digitized and form a spectrum on the computer. And so that's how we obtain this data. So this data we're just scanning, turning on a pulse, or turning on the electric field. We repeat that about 1,000 times per point on this spectrum, and then just to build up some statistics, and we can scan over these. And our laser line width is about 100 kilohertz thanks to our our ULE cavity. Okay. The time's wrong. Whatever. Okay, so now we're done talking about the apparatus, or we've talked about it enough. We're going to talk about these experiments in probing correlations in thermal gases. So you might think a thermal gas is like the most boring thing in the world. There's not really that much going on. We're always talking about making quantum degenerate matter and exotic phases and all these other things. But the spin statistics theorem actually dictates how the wave function must be symmetrized. And if you remember, the pair wave function is really quite intimately related to the correlations. And even in this silly toy model that I've written down here, where you just have two particles and you can do your Slater determinant, you have this product and this epsilon factor that is -1 if they're fermions and +1 if they're bosons. You can already see correlations here with just two particles. For bosons, if X and Y are the same, you see this enhancement here. And if you have fermions, if X and Y are equal, then you have 0 probability, which means that you can never find these two particles in the same place, so to speak. This model is a little silly, but you can see that even in the two particle case, these correlations arise. And it's pretty amazing to me that something as simple as just the spin, the integerness or half integerness of the spin gives rise to these correlations. So we can get specific and start calculating using this many-body formalism that the pair correlation function in thermal gas should be something like this. And it's this, again, this epsilon factor is +1 if the atoms are bosons, meaning that you see this enhancement in the correlations. It's -1 for fermions, where you see this dip, and that is exactly the Pauli exclusion principle at work. And then for distinguishable particles, there's no correlations at all. And so the length scale of this enhancement or suppression is set by the thermal de Broglie wavelength, which is essentially the de Broglie wavelength of a particle with energy kT. So the average de Broglie wavelength of a sample, which is about 200 nanometers for strontium at 1 microkelvin. And so I point that out because if you look at our ruler here, that's smack dab in the middle of the range that Rydberg molecules can be used to probe. Okay. So again, for this experiment, we're going to make use of strontium's awesome properties and produce a classical gas using unpolarized strontium-87. So again, once we have them trapped, the populations of the 10 sublevels are approximately equal. And this is a pretty good approximation of an uncorrelated gas. And by that I mean 9 out of 10 times, two colliding pairs will be, or a colliding pair of atoms will have different magnetic sublevels. And so they won't see any correlations. We can spin polarize strontium-87 by using optical pumping. So we apply circularly polarized light to this 87 sample here and can shelve 90% of our atoms in the MF = 9½ state. And if you look at this spectrum here, you see this is a Zeeman split Rydberg line. You can see all these peaks that correspond to the lower M sub F levels. And then after we apply this spin polarization pulse, all the population moves over here. And so the explanation for these different heights comes down to some Clutch-Gordon coefficients. But if we we know what those are, and we can fit the spectrum to determine that the populations are about equal. And then also that we can get about 90% of our atoms in this state. And then of course, we have to use 84, like I mentioned, to sympathetically cool. And then, I don't know what that's doing there. But then of course, we can make a gas of distinguishable bosons, or indistinguishable bosons, just using strontium-84 and evaporating down. Now, the experiment that we're going to do is we're going to compare the excitation rates of indistinguishable particles, so either the bosons or the fermions, to the classical gas. And again, we're just going to use the fact that we have this highly localized wave packet in our Rydberg potential to probe the correlation function here. So you can think kind of like n = 30 corresponds to that point, 33 to that point, 36 to that point, etc. So hopefully we should observe the effects of quantum statistics as our Rydberg radius gets on the order of our thermal de Broglie wavelength. And so we did the experiment. We have a gas of 84 at about 650 nanokelvin and a gas of polarized 87 about 860 nanokelvin. And we measured spectra like this at different quantum numbers and integrated them. And we plot those integrals on these lines here. And so we'll go one by one. So at the top, we have the uncorrelated gas. And we see that there's some n scaling that we can fit, and we'll talk about where that comes from in a minute. But everything follows some basic n scaling. And so next we look at the fermions, where we would expect to see suppression at low quantum number. And indeed, we look and we have this line has the same slope, and we start to see as n gets lower, we start to see a suppression of the excitation rate from this expected n scaling here. And similarly with the bosons, we see a lifting off from this line. And so again, we are exactly probing as we change the quantum number, we're probing a different distance, and we go from 31 to 45 in the triplet S series, which gives us a range of 1400 Bohr radii to 3200 Bohr radii. And it's obvious from here that we're seeing an effect, some difference between these samples, and really the only difference is the quantum statistics, not necessarily the excitation or anything like that. So how exactly do we extract this pair correlation function from the data? And this is a big question. So well, we have to just basically figure out all the terms that come into the excitation rate of a Rydberg molecule. So for a given colliding pair, the excitation rate from some initial state to final state is given by Fermi's golden rule, where you have a matrix element of some transition operator, which in our case is the 2-photon transition that I was talking about, and then the modulus of that squared. And here we've integrated over the spectrum, so there's no need for the corresponding delta function to conserve energy. So if you have an initial scattering state with momentum k and a final Rydberg molecule state n at nu equals 0, then this thing in the Born-Oppenheimer approximation becomes the square of a Frank-Condon factor, which is the spatial overlap of the final state with this initial scattering state, and then some parameters here that depend on principal quantum number and laser parameters. So this omega is the laser intensity, this beta is a reduced matrix element, thinking about the Wigner-Eckardt theorem, and then this C is a series of Clebsch-Gordon coefficients. So the total rate is, as we always learn in Randy Hewlett's class, you have to sum over final states and average over initial states. So in this picture, there's only one final state, and we have to average over all the collision energies that are Boltzmann distributed inside our sample. And so we can do a partial wave expansion of this, of the initial state here, and I see you're looking. We can talk about it later. And essentially, you end up with something like this. So yes, the final state can have angular momentum, but essentially the angular momentum that you excite to picks out the L channel here. And so here's where we make use of the fact that this molecular state is highly localized. We can take, since it's so narrow and this is so slowly varying, we can take this as approximately a delta function, and out pops the scattering wave function evaluated at the Rydberg radius. And so in the front, we have some integral of this thing, which just depends on essentially the width of the wave packet, which is not constant, it's a function of n, so we call it ON. And then here we have exactly a ensemble average of two particle wave functions, which is exactly G2. And so if you want to ask, I have a bonus slide to show the exact correspondence, but I think it suffices just to say this, and when you see the data, you'll believe it. Okay, so finally we have to integrate over the trap. So yeah, the trap that we're using is harmonic, so the density approximation is the density profile is a Gaussian, which means that the density is not the same everywhere in the trap. And the molecular excitation rate goes as that gamma times the density squared. So when you integrate over the trap, you just do this integral. We know the trap frequencies and everything, so we can just say it's n. And we measure of course, we measure the atom number and temperature every time. So finally, the total integrated signal is proportional to this density factor times the the laser parameters times a matrix element times Klutch-Gordon coefficients times some Frank-Condon thing times G2, okay? And so to extract this, we don't know all of these parameters. We know the density, and in fact, in this experiment, we did everything we could to keep the density of the unpolarized sample and the polarized samples the same. But we're going to take a ratio between the, say, the fermion and the classical gas. And so if your densities are the same, that should cancel. You keep your laser parameters the same, those cancel. The matrix element for a given n is the same. This ON is also the same because the Rydberg potential doesn't care about isotope. And then hopefully everything will be left will be just G2. There's a small complication due to the fact that when you're exciting out of the unpolarized fermions, you're actually driving 10 different Rydberg transitions. And those all have different strengths due to the Wigner-Eckardt theorem, or due to Klutch-Gordon coefficients, however you want to call it. But we know what those are and we can calculate them. And so essentially the ratio of, say, the fermions, and this is the same for the bosons as well, to this classical gas is about 5.05 times G2. And so we can take our data, so we take this data and we take a ratio between the blue and the green and the red and the green, and then divide out this 5.05, and we get something that looks like this. And so here we have three different samples. So we have a 650 Kelvin, a nanokelvin 84, and we see that it follows its expected G2 pretty well. And then we have two different temperatures of 87. So we have 2.05 microkelvin and an 860 nanokelvin, and those both follow their own G2. But where this is really great is we can now take and scale everything by the thermal de Broglie wavelength, which gives this pretty cool, in my opinion, result where we can see everybody falls onto the same curve and obeys the quantum statistics. And so I'm pretty happy to say that this means that we can probe G2 using Rydberg molecules. And that's a pretty neat thing. And that was a lot of work to get that done. And so now that we've done this for a non-interacting gas, it'll be interesting to think about exciting heteronuclear molecules to study strong interactions. So what happens when we turn on interactions? Well, a pair of colliding atoms at any interaction has a node in the scattering wave function at the S-wave scattering length. And so it would be pretty interesting if we could come up with a combination of isotopes such as 8488, for example, where the node is going to be way out here at 1800 Bohr. And so 8686 also has pretty strong interactions, but our target initially was 8488. So we can prepare a mixture of 84 and 88 at 750 nanokelvin and selectively excite a chosen isotope to a Rydberg state. And we have that selectivity because of this 445 megahertz isotope shift of the Rydberg state. Like I said, we have a combination of isotopes at 750 nanokelvin. We can choose the ratio of 84 to 88 by just tuning how long we load the trap for each one. And we can go from a ratio of about 30 to 1 down to 1 to 1, keeping the total atom number fixed at about 500,000 and the total peak density of about 5 times 10 to the 12 per cubic centimeter. So 3-body loss is not a huge deal. The lifetime of the sample is pretty short, but it's not that bad. And so when we turn on our excitation lasers, say we have a sample that's 84 only, we excite 88, and we're going to get 88 dimers. Say we have 84 only, and we excite 84, we're going to get 84 dimers. Now, of course, if I have this mixture, which is about a 50-50 mixture, and I excite 88, I'm going to get some homonuclear pairs and some heteronuclear pairs. And so what we did is we just started with these three different systems, and in particular, this one has a very small number of 88 atoms inside. And so as we scan our laser over the 3 different samples, we observe a shift depending on which isotope we're exciting. And as we go down from 39 to 31, we see this shift go up. And this is indeed an isotope shift. And that in and of itself is proof enough that we're creating these heteronuclear Rydberg molecules. So it's kind of a fun thing to look at. There's actually an n scaling for this isotope shift, and we can kind of estimate what that is. So here's our n equals 39 potential again, where we've estimated the outermost lobe as a parabola, so a typical harmonic oscillator, and we can see that the Rydberg wave function and the harmonic wave function are pretty close, especially given how crude this potential is. So the binding energy, which is where we observe the shift, is the depth of this well minus this characteristic frequency, and then we can write down this potential as this, centered at the Rydberg radius and then down by a depth d. And so we would expect that the change in this omega due to a change in the reduced mass would be on the order of 1%, going from 88 to 84, say. And then we know that the shift in the binding energy is going to be proportional to the shift, or equal to the shift in the frequency. So we can do some Rydberg scaling tricks where you kind of pretend everything is is just n. You don't worry about any details. You just say, okay, so the depth of this well scales as the volume of the Rydberg orbital, which goes as n to the minus 6. The width of this well is the radius of the Rydberg atom divided by the number of lobes, which is n squared over n. So that's just n. You can approximate the frequency of this thing by this, just using geometry, and then you obtain a scaling of n to the minus 4. And so it's pretty interesting, I think, that this really crude approximation actually describes the data pretty well. So in the open symbols, we have a theoretical prediction of the isotope shift. The closed symbols are the data, and we fit that data to a power law, and we find that it's pretty close to n to the minus 4. And since that approximation is using the harmonic approximation and that breaks down over time, I'm pretty happy with that. And so not only is it interesting that we are creating Rydberg molecules and we can say that we know that we're making heteronuclear Rydberg molecules, but looking at the binding energies of these things is a pretty sensitive probe to the Rydberg molecule potential. And it also brings in some interesting ideas of the different angular momentum channels that we can excite. So how good of a tool will this be for looking at interspecies correlations? It's hard to say, or not too hard to say. What's important though is you need to know that you are exciting heteronuclear molecules. And when your isotope shift is large, as it is for n equals 31, you can see it's more than one laser line width, you can very easily stick your laser 200 kilohertz to the blue of your 88 line and know exactly I'm making heteronuclear molecules. But say for n equals 39, your isotope shift is 50 kilohertz, which is half a laser line width. Can't exactly resolve those two peaks. So you really have to just kind of brute force it and really decrease, say, the 88 density in a background of 84, such that you are sure, or pretty sure, that when you excite an 88 atom and it makes a Rydberg molecule, its partner is an 84 atom. And so the question is, how pure of an excitation can we make? And so what we did is we said, okay, let's look at the integrated signal again as a function of density. And so again, here we have this S and this, so we have this rate constant, which is all of those electronic factors and everything like that from before, all wrapped up into here because this is all one quantum number. And then you have the n squared density dependence of the homonuclear case, and then you have a product of the densities for the heteronuclear case, and then you pop out this effective volume that comes from integrating over the trap. And so I can normalize this equation by dividing out the square of the 88 density, and we should see how the signal, we would expect the signal to scale given a given ratio of 84 to 88. And so on this log plot here, I have what would be the constant contribution from 88, and then any excess we observe has to be due to heteronuclear Rydberg molecules. And so this point up here is probably where we want to work, particularly at a higher n, where we have about a 30 to 1 fidelity. So we have a 30 to 1 odds that we're making a heteronuclear Rydberg molecule. And so with that, I'd like to conclude. What we've done is we've made a really nice tool using Rydberg molecules to probe spatial correlations, and we used it to probe the correlation function in a thermal gas. And we also, in the process, ended up making the first ever observed heteronuclear Rydberg molecules. And in the future, we're installing this 1D optical lattice and I'm really looking forward to working with everybody over the summer on this, and looking at strongly interacting 1D systems there. And also we're going to look at strongly interacting Bose mixtures as well, just in a harmonic trap, and look at how we can start resolving rotational states of Rydberg molecules. And so I'd really like to thank my committee, and of course the group, the entire group, everybody that's been a student in Tom's lab has had a really big impact on my life. And you know, five months ago, I wasn't sure if I was going to be standing up here giving this talk. And I just have to say, all my friends and family have been really supportive in helping me recover and all that. So I couldn't do it without you, and I love you all. So thanks.
Great job, Joe. You talked a little bit about the model. You put up some expressions where you're summing over partial waves. Can you just tell us a little bit more about sort of what's in that model, what's not in that model?
Sure.
You did a lot of work on that, so I'd just like to hear your thoughts on it.
Yeah. So again, just thinking about the Fermi's golden rule picture, we can get a little bit more concrete here. So let's start by specifying the initial states. So the initial states are colliding pair of atoms with momentum k, shown here. They have an energy given just by h bar squared k squared over 2m. All the atoms are in the electronic ground state, and all the energies are Boltzmann distributed using just normal statistical mechanics. So you apply this transition operator, which is the two-photon transition, which contains all the information about laser polarization, et cetera, selection rules, blah, blah, blah. And then the final state is not just a Rydberg molecule, but it's a Rydberg molecule with a particular angular momentum lambda. And you have this rotational energy here. And so when you look at that Frank-Condon factor that I was talking about, it's just simply the overlap of the initial state with some parity given by this plus minus, with a final state that has a given angular momentum. And brushing a couple things under the rug, essentially you can insert the identity, aka expand this plane wave state in terms of partial waves. And that's why in that initial expression I didn't have any other lambda, because you get that selection for free by having this inner product between angular momentum states here. And this matrix element, or whatever you want to call it, turns out to be a spherical Bessel function times 2 lambda plus 1, and then you have this p, which enforces the particle statistics. So if you have bosons, let's say, only even partial waves contribute. If you have fermions, only odd ones contribute. And you can go through and perform the averaging, the thermal averaging, and sum over partial waves, and you get exactly the G2 expression that you would expect. And so you can see how the different partial waves contribute at different temperatures for bosons, fermions, and then distinguishable particles. So the distinguishable particles would be a half of the plus the minus, so the exponential part cancels and you just get 1.
And what's not in this one? Is this going to describe all systems, or is there some physics that might be important to our system that's not in this model?
Sure. I mean, not in this model would be, so this is just for plane waves, right? The strong interactions are not there. And then you can add in the strong interactions phenomenologically just by adding in a scattering phase shift. But that, as we know from what we were talking about at the beginning, doesn't describe really any of the wave function after you pass this node.
Towards small r.
Yeah, towards small r. So what Shuhei showed in his calculation is, maybe we see this big enhancement after the node, and that explains some of the data that we've seen, but that's definitely not there. Also, obviously, there's no spin in our model. Technically, this is a triplet, but everything's at zero magnetic field, so we excite to a single state, so we don't really worry about it. Learned that that's not such a great approximation recently, but yeah, I think that about sums it up.
How does the capabilities of this technique, how do they compare to something like anti-blockade?
You mean like in a Rydberg system?
Yeah, an anti-Rydberg blockade.
As a way to probe
There's a way to put a separation, looking at, pair Rydberg pair production.
Sure. I mean, so in particular, I think, let's say you somehow had an optical lattice that you could tune the lattice constant of. You could perform, or even optical tweezers, you could perform a nice experiment where you look as you move the two atoms together, you could see the blockade or anti-blockade show up, right? But that kind of depends on a well-defined initial state. And so when you have, say, this is where this technique really is good, is that when you don't have a well-defined initial state, you do have a well-defined final state. And so if you're talking about this anti-blockade thing, say you excite some Rydberg atoms, you have to integrate over all separations. And so to see that effect, it would just kind of manifest itself as like a weird shift, whereas we can say specifically that we're probing at a single distance.
You could do that with anti-blockade, right? You could tune a laser to create, and then you could immediately switch it to another frequency and say, oh, now I've tuned to a certain radius, a certain separation.
Yeah, sure. But I don't know what information that gives you necessarily about the initial state.
You'd either create two Rydberg atoms or not, and
Yeah,
depending on the separation of the atoms.
Yeah.
You need atom pairs.
That's true. Yeah, I've never really thought about that. I guess typically we're trying to avoid interactions, right? So, Jim?
So it's been a while since I thought about this, but I think if I recall, you're like pretty far from the Fermi temperature. Like
The coldest we get is like 1, T over T of 1.
So did you have to account for the change?
Well, so actually with fermions, it's all the G2 is the same always. There's no critical transition, right? So for bosons, the BEC is classical. Yeah. So we had to work hard to stay. We were like T over TC of like 1.5, and so we had to check to make sure that everything we did uses a thermal distribution, but it's really a Bose distribution, right? We had to check that shape of density profile didn't really change anything, and it doesn't, not to within the level that we can measure. Here, I can see if there's a. I don't see any questions in here. Does anyone else have any questions? Go ahead, Hanya. Sure.
A quick question. When you talk about non-interacting systems and or in the future
Mhm.
strongly interacting one-lead systems, what's the order of magnitude of this interaction strengths compared with the the Rydberg?
Yeah, I would say, I guess when I think about it, typically these interactions are more what I would call like a hardcore interaction. So I wouldn't say that there's necessarily like a energy scale associated with it. So particularly, well, like in the case of so in the case of this, say this like strongly interacting system here, once you're around the node here, it doesn't matter what your collision energy is. For every collision energy, there's this node here. And so that interaction, there's definitely no particles present, right? And then when you start talking about this 1D thing, you make a gas of tubes and you start increasing the confinement and you observe a transition from where bosons start to act like fermions. And essentially you have this hardcore repulsion at R equals 0. And so the types of correlations that like I said, the types of correlations that I think about are really kind of manifested due to this like hardcore repulsion.
There might be another way to think of that question too. So initially, say we got into more exotic type energies, and you were talking about maybe you had bound pairs in the ground state or something like that. Those energies are relatively small, kilohertz kind of energy scales. And then this probe, you have this optical photon that's exciting up to the Rydberg, and it's going to break any of those pairs or anything. So you really will. I think it still will work fine even if you have those kind of strong interactions there as you sort of inject an excitation to a highly excited state.
So eventually we still expect this like thermal gas type of behavior.
Not necessarily.
No, I think, I think you could imagine,
It all,
say the initial state
Yeah,
has some
exactly.
other structure.
it depends on the, so
Yeah.
you're probing the initial state, right? And so the reason we're talking about thermal gases so much is because that's the easiest thing to work with. So, but if you come up with some, because you're summing over final states, so you're summing over these rotational Rydberg molecule states, but you have to average over the initial state, right? And so that initial state, I mean, let's say it could be a mod insulator in an optical lattice where you have one atom per site. And so that initial state is just, instead of an ensemble average, it's just an expectation value like you do in quantum one, right? So.
Thanks.
Yeah, when you were calculating that 5.05 ratio, why do you expect it to be the same for fermions and bosons?
Oh, that's a good question. So the answer is that a Clebsch-Gordon coefficient comes from an overlap between let's see, I don't want to say this. It comes from the addition of angular momentum, and but really what's going on is you have the coupling of the electron spin to the nuclear spin, but you can express those two. Let's see. You can express the two spin system in two different ways. You can talk about the uncoupled projection where the spins are just have their own m's, and then you can talk about a coupled projection where you have a total angular momentum and then a projection of that angular momentum along the quantization axis. However, when you're in what's called a stretch state or like a maximal state, when you have both m's that you're coupling in the highest possible level, that is the same as a boson, essentially. So the fact that we excite along this stretch state for polarized 87, and in my thesis I explicitly work out exactly how to prove that, but since the intuitive way to think about it is you're going from a stretch state to a stretch state, so the nuclear spin is essentially uncoupled from the electron spin. It doesn't matter.
So you talk about using the unpolarized fermions as the classical or distinguishable gas.
Mm-hmm.
In what sense are they distinguishable?
Sure,
There's
so
still 87 fermions.
Indeed, you could not tell. They're distinguished. I use the word distinguishable interchangeably with uncorrelated, which maybe is not right, but it is helpful. So the reason that they are uncorrelated is because the pair wave function for fermions always has to be antisymmetric under exchange of labels. So if they're in the same, if the spins are in the same state, then that's even. So you have to have an odd spatial wave function to see Pauli exclusion. But if you have, say, an up and a down, you can make a triplet a triplet even spin part of the wave function, and then have what am I saying? You can make a singlet spin wave function and then have an even spatial wave function. And so that's what I mean, I guess. Yeah. They aren't forced to have an antisymmetric spatial wave function.
Right, they still obey the quantum statistics of identical fermions,
Yes.
but that doesn't restrict the
Yes.
form of the spatial wave function.
So you're gonna be able to blink the lattice, like with 1D tubes? Because I would imagine your oscillator.
Yeah. I mean, our data rate's like 4 kilohertz. Lattice frequency is gonna be up there. Yeah. So I don't know. We'll see. I mean, you could probably just do it in the lattice. You just deal with broadening. It'd be some AC structure shift or something. But again, you're just integrating. You integrate the signal. It doesn't really matter what it is, right? So even if there's an AC stark shift, and actually that would tell you where in the lattice it is. So maybe there'd actually be some interesting structure along that broadening.
Any other questions? Okay. Great. committee, do you have any other questions? Do you want Joe to stay or for?
No.
Okay, well, maybe everyone could excuse us and Joe.
Oh, I'm
Actually,
out?
stay in for
I'll
a minute,
stay,
stay in for a
yeah.
minute.
Here, let me turn off the